Okay, so before the break, we just looked at the idea of Bezier patches. Essentially, these are the same as curves and applied in a similar way. Okay, so we're going to move on in this second half to look at what we call B-splines. Now, Bezier curves, I mentioned, but a polynomial can have a number of changes of direction, which is one less than the degree. So let's say you've got a really wavy line with lots and lots of changes of direction, lots of squiggles in it. So what we could do is have a very high degree Bezier curve. But the problem is there's that computational cost there. The higher the degree, the bigger our matrices are, and students start to get unwieldy. So this is when we come to B-splines, which is short for basis splines. And essentially, these are several Bezier curves joined end on end. Okay, so rather than having a single high degree Bezier curve, you have lots of low degree Bezier curves just joined onto each other. Okay, so what we say is a k degree B-spline curve. Okay, so this time I'm going to, instead of using n for the degree, I'm using k, defined by n plus 1 control points, will consist of n minus k plus 1 Bezier curves. So an example of that, if I had a cubic B-spline, so therefore k is 3, defined by 6 control points, so my control points would be P0, P1, P2, up to P5. So Pn, n is 5 in this case. So in other words, 6 minus 1. Well, this will mean we'll have 3 Bezier curves joined together. Sort of mathematics to do so. Okay, so we're going to make some assumptions in deriving our B-spline curves. Okay, what we're going to say is the final point on the first Bezier curve is going to be the same as the first point on the second Bezier curve. So in other words, there's no gaps, they join together. So as soon as we've done with one Bezier curve, we're right at the start of the next one. And that's known as C0 continuity. The second assumption is the first derivative at the end of the first Bezier curve is the same as the first derivative at the start of the second. So in other words, the gradient at the end of one is going to be the same as the gradient at the end of the other. So it's not going to be like a kink. Our curves are going to be nice and smooth. There's going to be no sort of abrupt change of direction. Okay, as well as the first derivative, we also have the second derivative. So that's known as C2 continuity. Okay, so those are the assumptions. So in other words, we want a nice, we don't want our line broken up, and we want it nice and smooth. Okay, a B-spline is defined in a similar way to Bezier curve. So you remember I had a sum of Bernstein polynomials multiplied by the control points. We got something similar here. So ST is my spline. So for a value of t, we're going to have some spline. Okay, PI, that's our control points. This NIK, these are what we call basis functions, where B-splines gets its name. So the NIK, okay, these are all going to be basis functions. Bernstein polynomials are a form of basis function. And these are defined by using this Cox-de Boer recursion formula. Now, this is quite complicated. It's not something which I'm going to ask you to do. Okay. If you've got a spare time on a Saturday night and you're a bit bored, you can do it. But yeah, it's good for you. It's nice algebra. But it's not something you'll be asked to do in an exam. So don't worry too much about that. Okay, so our basis function, this is the same sort of numbering convention as before. So where j, or in this case k, is 0, that's our first sort of first basis functions. So ni0, this is basically a switch. It's either on or off, depending on what we call a knot vector, and I'll come to that in a minute. Okay, so when we're at the far left-hand side of our triangular scheme, those values are either going to be 0 or 1. They're going to be on or off. For all other values, we have this scheme. Okay, and this is similar to de Castiglio's algorithm. It's similar to that triangular scheme. Okay, so on the far right, this is our B-spline, N0K. Okay, that's what we're trying to calculate. Okay, that is a combination of these two. Okay, and each of these is a combination of 2, and we keep going down until we're at this far left-hand side. Okay, the horizontal arrows denote we multiply by t, which is our parameter, minus ti, divided by ti plus j minus ti. Now, wherever you see a subscript on a t, it's not, sorry, I should not use the word not, we'll see why in a minute. It isn't the same as the t parameter. So these subscripts is not the same as a t parameter. These t subscripts are what we call knots, K-N-O-T, as in knots on a piece of string. Okay, and depending on the relationship between our t parameter and these knots, depends on which control point has an influence on our B-spline. Okay. Okay, so this is where it comes to the knot vector. So I've got to be careful about using the word N-O-T, not rather than K-N-O-T. Okay, t subscripts are taken from a sequence called a knot vector. Okay, these are just a vector of numbers, monotonically increasing numbers. So each number is going to be greater than or equal to the number preceding it. Okay, the knots that our parameter t lies between determines the basis function for the B-spline at that point. Okay, so t, remember t is a parameter. With the B-splines, it doesn't have to be between 0 and 1. Okay, but later on when we apply it, we make it so. It doesn't have to be. Okay, and depending on where our value of t is, depending on which knots that it falls between, will depend on the basis function. Okay. How many knots do we need? Now, a knot is just a number. Okay, so here we have our vector, t0 to tm. These are just going to be numbers. Okay. The number of knots is related to the degree and the number of control points. So m, which is the subscript of the last knot, is equal to the degree of our B-spline plus n plus 1. N is a number of control points. Well, n plus 1 is the number of control points. Okay. So, for example, if I had a cubic B-spline, so that means k is equal to 3, defined by using 5 control points, P0 to P4, so this means n is 4. Okay, so k is 3, n is 4, plus a 1 means I need m to be 8. Okay, so remember we start at 0 and we go up to tn. So it's going to be a knot vector could be 0 up to 8. Okay, and wherever my t is, my t parameter would be 0 to 8. Depending on where it is, which two knots it falls between will change our basis function. Okay, so there are many different types of B-splines. By far the most popular or common are what we call a uniform B-spline. Uniform means that the knots are sort of same spaced apart. So you can see each one of these knots is just one more than the last. So that's a uniform knot vector. It doesn't have to be. I could have 0, 2, 3, 7. You know, we could have big jumps between them. But if the difference between two successive knots is the same, it's uniform. Okay. So for example, if I wanted a quadratic B-spline, which is defined by 3 control points, then I need 5 knots. well, I'd actually need 6 knots, but there would be, n would be 5. So for example, you'd have 0, 1, 2, 3, 4, 5 would be our knots. Okay, in the B-spline curve, sum from I equals 0 to k. So in our case, k is 2. It's quadratic. So we have ni2. So our triangular scheme is this. So this is what we're trying to calculate. This is our basis function, which is a combination of those two, and each of those two are a combination of these. Now the ones on the far left, depending on our value of t, where it falls between these numbers, will turn these off or on. Only one of these will have a non-zero value. So all of these will be 0 apart from one of them, which will have a value of 1. So for example, I'm just going to step you through a derivation. By the way, you don't have to do this. You don't, in an exam, you wouldn't be asked to do this. So NO2, okay, the horizontal arrow is t minus ti over ti plus 1 minus ti. Okay? The diagonal arrow is a bit more complicated. So that's the horizontal arrow. Okay, if that for this knot vector, there's t0, t1, t2, t3, etc. Okay, so that's a horizontal arrow, and that's using tn01. That's a diagonal arrow using n11. Okay, so horizontal, diagonal. Okay, this is very similar to Castiglia's algorithm for Bezier curves. Okay, well, each of these, n01 and n11, is given in those square brackets. Okay, so again, we have a slightly more complicated coefficient before the n basis vectors. Okay. So that's, okay, so we can actually simplify this. You can see we've got an n10 there and an n10 there, so we can simplify that to that expression. Okay, well, that's not the end of it. Okay, because these n values here are either going to be 0 or 1, depending on where that t falls in the knot vector. Okay, so that's what I ended up with. So that bottom expression there is what we end up with. So for example, when our parameter t lies between 0 and 1, that's the first two knot vectors, sorry, first two knot values, our NOOT is going to be equal to 1. The others are going to be equal to 0. Okay, I'll show you where that comes from. That comes from here. Okay, so if t is between t0 and t1, which was 0 and 1, our n, ni0, so n10 will be 1, else it's 0. So it's like turning it off, switching it off and on. Okay, so when our t value is between the first two knots, okay, NOO is 1, all the other ends are 0, so we just got a half t squared. When t is between the second and third knot, okay, NOO is 0, N10 is 1, N20 is 0. Okay, so this is then 0, this is 1, that's 1, and that's 0. And we have that function. When t is between the third and fourth knot, third and fourth, third and fourth, okay, NOO is 0, N10 is 0, N20 is 1. And we have a different basis function. Okay, so where our t is changes our basis function. Okay, and we could do the same for other values of I. Okay, that's quite a lot of algebra. It's not something I'm going to get you to do. If you're interested in it, there's in the appendix at the back. I've done it for a cubic. No, I've done it for a quadratic, which took ages. So it's a lot of algebra. Okay, so these are our basis functions. Okay, you notice. Okay, so let's say our knot. These are our values for our knots. Okay, if t is between 0 and 1, we have this. If it's between 1 and 2, we have that. 2 or 3, we have that. Okay. Second basis function will be between we use different knots. So depending on where you are in the B-spline, will change what knots you're using. Okay, there should be a little pattern between these. These are all the same, except we're subtracting one from what we're taking away. So, for example, you look between these two, we have a half t minus 1 squared. Well, that's a half t minus 2 squared. This here is the same as this, except for we got t minus 3 as opposed to t minus 2. So in other words, they're just shifted along from each other. They're the same shape, just shifted to the right. So that's your basis functions, similar to Bernstein polynomials. And there's your basis function. So on the bottom we have our t. So in this case, t goes from 0 to 5, not 0 to 1. Our knots are at 1, 0, 1, 2, 3, 4, 5. So let's say t was 1.5. Okay, so it falls between 1 and 2. That green section there would be our basis function for one of them. So you can see they're just shifted along. Now, why have I changed that graph to this? Well, the area between those two black lines, that's where we have three basis functions. So if I was to draw a horizontal vertical line along between these two black lines, I have three basis functions. Elsewhere, I've just got 2 or 1. So our B-spline is only actually defined between these two. It's not defined outside because we don't have enough basis functions. Okay. Same with Bezier curves. We don't do it all like that. What we want to do is we want to end up with a matrix equation. And it's actually as simple as the Bezier curve. So whilst it's quite tricky to understand the derivation, calculating B-splines is quite easy. Okay, so from this, we can see but our B-spline is only defined between the knots 2 and 3. Okay, so between the knots 2 and 3, these are my three basis functions, similar to Bernstein. Okay, so you can see we have t minus t2 squared minus 2 t minus t2 plus 1. Okay, so written in matrix form, okay, we're doing it in terms of t minus t2. So we've got 1 lots of it there, minus 2 lots of it there, we've got 1 lots of 1 there. Okay, so that gives me my top row. And I multiply that by a half because that's where that half comes from there. Okay, here we've got minus 2 lots of t minus t2 squared, which is that bit, plus 2 lots of t minus t2, which is that 2, plus 1. And on the bottom, I just got 1 lots of t minus t2 squared, which is there. Okay, so this is my B-spline for a quadratic for that knot vector. Okay, so P1, P2, P0, P1, P2 are my control points. This matrix here, this is my quadratic B-spline. And again, we've got the same right-hand side vector. So B-splines are more complicated than Bezier curves, so they're no more complicated to actually calculate. They're very, very clever things. So in general terms, because we can have 100 control points, okay, so depending on how many control points you have, will depend on what part of the spline you're at. Okay, so we say, okay, this is part of the spline, we'll use different control points. And we'll do an activity in a minute to show that. Okay, so there's the here's a MATLAB function to actually draw a B-spline. P are your control points, T are your parameter values. Okay, you can have as many control points as you want, as long as it's greater than 5 or greater than or equal to 5. Okay, so what we do is you loop through the basis function and calculate a different B-spline curve or a different Bezier curve depending on where you are in the B-spline. So at the beginning, okay, we're using, so let's say when I is 1, we're using P, the first, second, and third columns of P times n times t. Then when I is 2, we're using the second, third, and fourth. When I is 3, we're using 3, 4, and 5, 4, 5, 6, etc. So you're moving along your control points. And this bit just adds your current B-spline to the end of your spline. So you're just adding lots of Bezier curves to the end. Okay, so there's your output. Hopefully I've got a demonstration here. Right, so I'm going to use, I'll talk about open in a minute. Okay, so what I'm going to do is sort of start a few. Okay, so there's my first sort of curve. Okay, I've got 4 control points and I've got 1 curve. If I click another control point, I'm adding another control point, and that blue curve follows it around. So I can just keep clicking as much as I want, and I could define that blue curve keeps getting defined. Okay, so rather than having a very high degree Bezier curve, I've only got a quadratic B-spline, but I'm having lots of Bezier curves one after the other. Okay, so there you are. So you can just draw, you know, you can add more and more control points to make more and more wiggly lines. So B-splines are very, very useful. What you might notice is, I don't know whether you can see here, but the blue curve doesn't start at this point. Okay, it starts a bit way along and it ends halfway along the last line here. Okay, now, why is that? Well, this is the reason. Okay, so the blue lines here are my basis functions. Okay, and these sort of horizontal red lines here are the boundaries where there are at least 3 basis functions defining that point. So if I was to add up the basis functions, here they all sum to 1, but outside of these 2 red lines, they don't. So our B-spline is undefined outside of those vertical red lines. Okay, so that's why it doesn't quite get to the end. My last first and last control point. Okay, to get over that, we can look at what we call open uniform B-splines. Okay, so uniform B-splines aren't defined for all of the range of our knots. It's only defined where we have at least 3 basis functions overlapping. Now, open uniform B-splines gets over this by padding out our knot array. Okay, in other words, okay, have a look at this knot array. So this is for a quadratic B-spline. What we can do is we can put the first 2 knots to be the same as that number there. Okay, so these 4 internal knots, okay, that was where originally my B-spline was defined for. Okay, so we can pad out the first 2 knots to be the same as that number, and the last 2 knots to be the same as that number. So the first K knot, so K is your, because it's quadratic, that's why it's 2. If it's cubic, it would be 3. Okay, we can just pad it out. And this is what happens. This is what happens to our basis functions. It skews them a bit. Okay, so if you had to calculate this now, if you are bored on a Saturday night and you want to have some fun, go away and calculate this. You can, in the appendix at the back of these notes, I think I've included it, and you can see there's quite a lot of algebra involved. But that's what you get at the end of it. Okay, so you can see all of these, if I add them all up, will sum to 1. But they're no longer symmetric. The ones at the beginning and at the end are asymmetric. Okay, that's your quadratic. Okay, so the ones at the beginning and at the end are different. So what this means is this middle one was the same as the one we had before. Okay, so that's our matrix equation for our B-spline, the one before. The one at the very beginning is slightly different, has a different matrix. This uses the first, so P0, P1, P2 control points. Okay, so if at the beginning you have to use this one. Okay, so when so we say spline 0, it's going to be that's the first one. Spline 1 through to n minus 3, but n is number of control points minus 1. Okay, we use the standard one, and the last one, we use this one. Okay, so that's the MATLAB code for a B-spline. So this time we've got 3 different m vectors, depending on whether at the beginning, in the middle, or at the end. So the one at the beginning, calculate the first Bezier curve. That uses columns 1, 2, and 3, multiplied by M1. Now, M1 was just this square matrix here. So that's that one. Then, from 2 to n minus 3, we've got all the ones in the middle. We keep calculating them using different columns, and then just add it to the end of our spline, our S. And at the end, we use M3, and again, add it to the end. Okay, so if I go back to my demonstration, same program, but this time I'm going to use a closed one, an open one. Okay, so if I click at the beginning, if I click a few, oops. Oh, I think I accidentally clicked the wrong way. Okay, I'll try that one more time. Okay, so as you can see, the curve goes right to the end. Now I can just keep clicking to my heart's content, keep making a squiggly curve. Okay, now, as you can see, the open uniform one goes right to the end. Right, last thing for today, if you just turn over to page 3, we're going to calculate an open uniform B-spline. Okay, so remember I said depending on where you are, will depend on which one you use. So I've also copied out the matrix equation here. Okay, you might need extra paper for this one. Okay, so an open uniform B-spline is defined by 5 control points, P0 to P4. And I've given you the coordinates of those 5 control points. Mark the control points on the axis below, and calculate the points on the B-splines S0, S1, and S2 for those different values of t. Okay, so we'll start off by marking out the points on the axes. 0, 2, 3, 8, 5, 2, 7, 8, and 9, 2. So those are my control points. So it's going to be some sort of squiggly line. And I mentioned you probably need extra paper for this. Not enough room to busy working out. Okay, so S0 for t equals 0. Now if I look here, this is my S0. So it uses P0, P1, and P2. So the same with the Bezier curve, you've got P0, 1, 2, P1, 3, 8, P2, 5, 2. So each column of that matrix is a control point, P0, P1, P2. So then that's multiplied by a half of this matrix. Okay, then that's multiplied by t squared, t, and 1. So because t is 0, t squared is 0, t is 0, and we've got a 1. Okay, so we multiply the first two matrices together. What we've got 2 minus 9, which is minus 7, plus 5, so that's minus 2. But remember, we're halving it, so that'll be minus 1. So that's just first row, first column, 2 minus 9 plus 5. So now we've got minus 4 plus 12 plus 0. So that's going to be 8. But remember, we're halving it, so that's 4. Don't forget to halve it. What else? On the last one's easy. We just got 1 times 2. Because as we go down, it's 0 and 0. So half of 2 is 1. Okay, second row, we've got 2 times 2 minus 3 times 8 plus 2. So that's 4 minus 24, so that's minus 20, plus 2 minus 18, but we're divided by 2, so that's minus 9. Next, we've got 2 times minus 4, which is minus 8, plus 8 times 4, which is 32. So that's 24. Half of 24 is 12. And finally, it's just 2 times 2 is 4, half that is 2. Okay. Multiply by 0, 0, 1, so it's just the last column. So that's 1, 2. Okay, so our first point on our B-spline is at 1, 2, which happens to be the same as the first control point. That's just making the point, sorry, no pun intended, but that's just making the, just showing the concept that when t is 0, you're at the first control point. Okay, what about when t is 0.25? No point doing more work than we have to. Okay, so it's going to be the same first two matrices which we calculated here, so just use that. And 0.25 squared, well, that's 1/8, isn't it? 0.0625. We've got 0.25 and we've got 1. How we multiply those two together? So we've got minus 1 times 0.0625 plus 4 times 0.25 plus 1. 4.9375. And on the bottom, minus 9 times 0.0625 plus 12 times 0.25 plus 1. Oh, plus 2 actually. 4.4375. Okay. What about when t is equal to 0.5? Same first matrix. 0.5 squared is a quarter. We do this similar. So whilst Oops, sorry. So whilst the derivation of these is actually quite involved, when it comes to, if we got them in matrix form, when it comes to calculating them, it's just multiply some matrices together, apply your control points, and just do the calculation. Okay, and finally, 0.75. What's 0.75 squared? 0.5625. Okay, so that's for t is equal to 0, 0.25, 0.5, and 0.75. Okay, now we're going to calculate the second S1. So this is still in the same B-spline, but now we're using different control points. We've gone to the end of our first 3 control points. Now we're going to use, instead of using P0, P1, P2, we're going to use P1, P2, P3. Okay, so I'm going to call this S1. Okay, so now what we have is P1, which is 3,8, P2, which is 5,2, and P3, which is 7,8. That's P1, P2, P3. Up here we have P0, P1, P2. Okay, so we're now using different control points. We're stepping along to use different control points. That's multiplied. Now this is going to mean we have a different matrix. So that's multiplied by this one, which is a half. 1 minus 2, 1 minus 2, 2, 1, 1, 0, 0. And because t is 0, we're multiplying that by 0, 0, 1. Okay, again, if we multiply the first 2 out, what do we have? We have 3 minus 10 is minus 7, plus 7 is 0. We have minus 6 plus 10, which is 4, but remember a half in it, that's 2. And 3 plus 5 is 8, but half is 4. And on the bottom, 8 minus 4 is 4, plus 8 is 12. We halve it, give us 6. Minus 16 plus 4 is minus 12. Halve that, minus 6. And finally, 8 plus 2 is 10. Halve it, give us 5. Okay, so using the P1, P2, P3 this time, when t is 0, we get 4, 5, which happens to be the same. No, it doesn't happen to be the same, sorry. Ignore me for a bit. That's the start of the next Bezier curve. And we do the same for t is equal to 0.25. We've already done the hard work with multiplying these two together. And that's what we're going to multiply by. So 0 times that, just ignore that. 2 times 2.5 plus 4. 4.5. 6 times 0 minus 6 times 0.25 plus 5. Okay, now we carry on. Again, how work's been done, so just copy that matrix down. And that's our vector we're multiplying by there. 0.5 squared, 0.5 and 1. So that's 2 times 0.5 is 1 plus 4, so that's 5. 6 times 0.25 minus 6 times 0.5 plus 9. Okay, so what we're doing, we're calculating lots of coordinates. These coordinates are points on our B-spline. Obviously, a computer would have a lot more values to t than this. We're only doing it for a few because, don't want to bore you to death. Doing a good job of that already. But a computer would have lots of different values of t. Okay, the more values you do it for, the smoother your curve is. Okay, well that's the middle sort of B-spline using the middle basis functions. If we had a lot more, control points, we keep using this middle one. But because we've only got 5 control points, now we have to switch to the last one. Okay, so Rn is 4. Okay, so we continue for this one. I is equal, when I is greater than or equal to 1, to n minus 3. Well, n minus 3 is 1, so we've only got one of those. So S2 is Sn minus 2, this one. So now we switch to this one here. So for the third one, okay, so now we're using P2, P3, and P4, which is 5, 2, 7, 8, and 9, 2. That's multiplied by a half in the final matrix. So what we've got here, we've got 5 minus 21, so that's minus 16, plus 18, so that's 2, divided by 2 is 1. Minus 10, add 14 is 4, 2. 5, add 7 is 12, divided by 2 is 6. And the second one, we've got 2, minus 24, so that's minus 22, add 2 is 18, so that's minus 9. Minus 4, add 16 is 12, 6. And 2, add 8, 10, so that's going to be 5. Okay, and we do similar. Okay, just done them quickly in my head. Okay, so I did the remaining three quickly in my head. I didn't use a pre-calculated MATLAB program to do that at all. Right, so that's the final one. So hopefully you get the idea. So what we've done is we've calculated lots of different points. Okay, so what we can do now is we can plot these points on that axis. So on your axis here. So starting at the top. Okay, I'll do this off camera just so you can still copy that down. Okay, so the first one was 1, 2, second one was 1.9375 and 4.43. Okay, 2.75. Okay, so if you plot them, you get something like that. Okay, I'm going to do it a bit better than that. Let's go back to HDMI. That's what you should end up with. So here's one I did earlier type thing. Okay, so each of those black dots are what we just calculated. And the blue line is, okay, I've done it using lots more t values of t. So you can see we've got a nice squiggly line to those control points. Right. So just to bring out the solutions there. So just a load of matrix multiplication, both Bezier curves and B-splines, very similar. B-splines are just lots of Bezier curves sort of joined together. Right, so just to go for the assignment once again. Question 1, I've already showed you that, it's on one of the slides. Question 2, very similar to what we've done on this activity sheet, except for it's a cubic, and I'm giving you different control points. Asking you to calculate the coordinates of the point on the Bezier curve for these values of t. Okay, and then part B, write a MATLAB program to do that. Okay, using 100 values of the parameter t. So 0 to 1 in steps of 100, in other words, or 101 values, doesn't really matter. Okay, so 1 and 2, okay, they are required, and so is 3 part A. So write a MATLAB program to reproduce that arrowhead. It's a bit of trial and error. You don't go straight there. You sort of mess about with up a bit and down a bit and stuff like that. But that's what you've got to try and recreate. If you want to do the additional task, if you want the more marks, the full marks, you then apply rotation and translation, and then you can fill it. Any questions on that assignment? Any questions on anything we've done today? None at all. So you can all derive those methods. Then. Good. I'd like to hear that. Okay, I'll see you all in the labs next week then.